we had few equations in chapter 4, if I remember, I think chapter 4. One of them it says V equals V0 plus AT. Remember those equations? X equals X sub 0 plus V average times T, or instead of V average, it's 1/2 V final plus V initial times T. You also have X equals X sub 0 plus V0T plus 1/2 AT squared. And the fourth equation, V final squared equals V0 squared plus 2A times delta X. Instead of delta X, you can write that X final minus X initial. These were the four equations, I think, in chapter, or 5 equations. We looked at them in chapter 4 or 5. Let me just take a peek so I can tell you exactly which chapter. Does everyone remember seeing these? You guys remember them? Yep. Where are they? It was chapter 4. I was right. It is chapter 4. X equals, well, this actually motion 2-dimension. Yep. X equals X sub 0 plus V0T plus 1/2 AT squared. V equals V0 plus A times T. They're dealing with 2-dimension here, projectile. It could be actually chapter 3, to be honest with you. It could be chapter 3, because in 4 we're dealing with 2-dimension. That's vectors. The book usually has a summary in them at the end. Let's see if it's in the summary chapters. The 4 equations. Maybe not. It is chapter 4 apparently, yeah. It is chapter 4. That's the 4 equations. Anyway, I don't want to flip this and keep getting people dizzy watching the video while they're looking at these. But those are the 4 equations that we spend weeks on them. Chapter summary. Let's see. I know there's a table, nice table in our book. I just don't know exactly where, with all these equations put in them. The book puts them in a nice frame there. Right there, it looks like this. V equals V0 plus AT. X equals X sub 0 plus 1/2 V0 plus VT. X equals X sub 0 plus V0T plus 1/2 AT squared, and that's the last one. Well, when things are spinning, are rotating, this is linear. When things are moving, a car on the ground, a bicycle. But when things are spinning, we're not really moving. The wheels are spinning, you know? But like you go to the dentist, you see the drill in your mouth, you can hear it spinning, but it's not going anywhere. You see the bit on that drill is spinning, or if you're drilling a hole at home using your drill there, you can see that bit is spinning there. So these equations will change a little bit. We no longer, so V is actually the linear velocity. A is the linear acceleration. And X is what? The position, the linear, on the ground. How far did you travel? A plane touched the runway, is going to slow down, come to a complete stop. You can see the distance traveled, 5,000 feet, 4,000 feet before it stopped. That's your linear disposition. How far did it go? Linear acceleration, if it's slowing down, the acceleration is decreasing. Your velocity, how many meters per second, how fast are you going? When you come to land, you're going about 180 miles per hour. We can convert that by dividing by 2.24. You're coming roughly about 80 meters per second. Then you're slowing down, you're slowing down, you're slowing down until you stop. Your final velocity is 0. These are linear velocity. We're dealing with angular position, angular velocity, angular acceleration. What does that mean? When a wheel is spinning, you're not going on the ground. You got centrifuge, you're at a medical lab, and the centrifuge is spinning there. The unit is not going anywhere, it's still sitting on that table, but it's traveling in a circular path. That's called angular position. How far did you travel? We measure the position is no longer x, we call it theta. How many radian? So angular position we use theta for that. How far did you go? If you did 6 revolutions, for example, we say, what is your theta? What's your angular position? How far did you travel? Well, we know each turn, each revolution is how many radian. When you start from this point and you go around the same spot, clockwise or counterclockwise, doesn't really matter. It's positive versus negative. How many radian do you travel? That's 2 pi. So if you get 6 revolution, that means 6 times 2 pi, and that's your distance traveled in radian. That's called angular position. Again, if you travel clockwise, that's a negative. Counterclockwise, that's positive. Where's pi here? Pi, where'd you go? Oh, I see it. So we travel a distance of 37.7 radian. We measure the distance, angular position in radian. How many radian did you travel? Again, positive versus negative. Counterclockwise, theta is positive. If we do what? Counterclockwise. Theta is negative if we do what? Clockwise. That's what angular position. Now again, you're spinning the wheel there. You're changing the speed of that. Your car, for example. You step on the gas pedal, you see the RPM goes up higher. The wheel's still spinning at a faster rate. That's called angular velocity or speed. And for that, we use the letter W, angular velocity. And the fast, if for example, if it's your bicycle there, the faster that you're spinning there, the wheels are spinning, the faster you're moving on the ground. Why? Because we do have a relationship between the linear versus the angular. The angular is how fast you're spinning, that's your W. The linear is how fast you're moving on the ground. So if this is what V is, the wheel is sitting on the ground, and how fast, if somebody has a gun, and like speed gun, and monitoring you how fast you're moving on the ground. We're taking your speed there. That's your speed on the ground. That depends on 2 things. It's the radius of the wheel and how fast the wheel is spinning. So the angular or linear speed is related to the angular speed here using this equation. V equals R times W. So there's a relationship between how fast the bicycle is moving or how fast your car is moving in relation to your RPM. The more RPM, that means the higher rate, RPM, revolution per minute, that's speed. The higher the number, the faster you're going to move. The lower the number, the slower your speed. Using that equation, V equals R times W. And acceleration, we use angular acceleration. You take your CD, you want to play it. You open the cover, you put the CD on. Initially, the CD has 0 RPM, it's not moving. Well, to play, you got to get it to a certain speed. It could be 33 revolution, RPM per minute. Could be, I don't know what the number for a CD. But you have it to get to a spin to a certain time before you can actually start listening to it. There must be an acceleration because you went from 0 velocity to, let's say, I don't know, 33 RPM. So there must be an acceleration. We call that alpha. And just like linear speed is related to angular speed, the same thing with linear acceleration. Alpha is how fast the acceleration as you're spinning is related to the linear acceleration. This is A, and this is R. The linear acceleration is equal to what? R times alpha. The linear acceleration is related to your angular acceleration by using that equation, R times alpha. So the good news here, when you're dealing with these equations, we can create now 5 more when things are spinning in a circle. All I have to do, go to these equations, and every time I see x, I'm going to replace it with theta. Every time I see v, I'm going to replace it with w. And every time I see a, I'm going to replace it with alpha. Angular acceleration, angular speed, angular displacement or position. And if I do that, look at the first equation. So the first equation here, replace v with w, replace v with w again, a with alpha. That becomes one of the equations. The second equation, right here, replace x with theta. This one, theta 0, plus w average times t. This one here, theta equals theta 0 plus 1/2 w plus w0t. This one, theta equals theta 0 plus w0t plus 1/2 alpha t squared. This one, w squared equals w0 squared plus 2 alpha times delta theta. And the last one, w squared is the same one as the one above it, but instead of saying delta alpha, I'm going to write delta theta, I'm going to say theta minus theta 0. So these equations are good just like the linear ones. We use these when we have circular motion. By the way, I remember the name of the plane. Stealth bomber. I just looked at it, it just came to me. If you look at the wings, that's what they look like. Took me a while to think of it. I wasn't even thinking until I looked now. And it just, boom, the name came to me. So one example on that, then I'll come back to my torque and angular acceleration. Okay. You're in your car and you want to pass somebody on the road. Initially, your car running at 2,000 RPM. RPM stands for revolution per minute. You stepped on the gas, and after 5 seconds here, your RPM is, I don't know, 3,000 RPM. Can you find the angular acceleration? Do we know what the angular acceleration? That engine has to spin fast to get the wheels going. What is that acceleration? So basically, looking at the wheel of your car spinning at 2,000 RPM. Now you get the wheel spinning 3,000 RPM. And if you want to make it actually interesting, let's put them on those, when they test the miles per gallon, you've probably seen them. It looks like a long tube, one on each side, the tires, and the car is spinning, but the car is not going anywhere because the thing under spins with it. So the car is not even moving in the linear direction. I don't care if it's moving or not. It could be on these two tubes for the front tires and 2 tubes for the back tires, and as the wheels are going forward, the tubes are spinning backward. So you're stationary, or it could be moving, it doesn't really matter. Because I don't want you to start thinking about linear velocity. That's why I'm using the tubes here. So now let's see, what do I know? I know the initial angular speed. 2,000 RPM. That's not good. RPM stands for revolution per minute. My W has to be in radian per second. So that's not good. I need to convert that. 2,000 rev per minute. So each revolution, how many radian? Each rev is 2 pi radian. Notice I put revolution on the bottom, not on the top. Why? So they can cancel each other out. Good. My answer in radian per minute. I want W to be in radian per what? Second. So I'm going to multiply that. I want radian in the bottom. And not radian. I want minutes in the bottom. And I want what on the top? Second. 1 minute has how many seconds? Oh, I put them backward. I want minutes on the top to cancel minutes on the bottom. Notice minutes on the bottom. 1 minute has how many seconds? 60. So what's my initial angular speed? 400 pi. That number is 400 pi. 4,000. 2,000 times 2 is 4,000. Divided by what, 60? 209.4 rad per second. Let's look at my final speed, angular speed, 3,000 RPM, 3,000 rev per minute. Again, I want revolution on the bottom, radian on the top. 1 rev is 2 pi radian. Now I have radian per minute. I need to get rid of minutes and make it second. Minutes on the bottom, I want minutes on the top, seconds on the bottom. 1 minute is 60 seconds. times 2 times pi divided by 60. I got 314.2 roughly rad per second. So here we go. We know what? We know the initial angular speed, 209.4 rad per second. We know the final angular speed, which is 314.2 rad per second. We know the time, which is what? 5 seconds. We're looking for alpha. Angular acceleration, alpha. Do we have an equation that will tie all these pieces together? All these four things? Let's look right here. W, W0, T, and alpha. W, W0, T, and alpha. Which equation here?
Top one.
Top one. Has all four pieces in it. So if I use the top one, I can find alpha. .300.2 equals 209.4 plus alpha times t. T we know is what, 5 seconds? Yep. .314 minus 209. 314.2 minus 209.4. 104.8 equals 5 alpha. Do we know what alpha is? 20.96, roughly 21 rad per second squared. Now, while I'm at it, what is the size of most tires on a car? If you go from the center of the tire to the edge of it, to the outside edge, not to the inside rim, to the outside edge of the tire, does anyone know what the dimension is? The tire is probably what, about this big? Roughly. Where's my ruler? Where'd you go? Maybe 2 of these? Yeah, about 2 of these. So let's say the radius is 30 centimeters to the edge of that. What is the linear acceleration? If you can monitor the acceleration on the ground, A equals R times alpha. We know what R, which is 0.30. We know what alpha, which is 21. Roughly 6.3 meters per second squared. So when you stepped on the gas pedal, your acceleration for the car is approximately 6.3 meters per second squared. So by knowing what the angular acceleration is and what the size of the tire is, we can tell you what the linear acceleration. So this is what angular acceleration versus linear acceleration. Because the topic here, torque and angular acceleration, and I want to make sure the students we inherited today, they didn't get a chance to cover that. Now at least you've seen it. Quick review of it. I'll stop here.